Okay, hold on, guys. We have to. It's recording now, so we'll stop talking about Shane. So if you want to continue all those negative things, you can just pick up after I stop recording after class. Okay. So Thomas, your question was, why is the EMF? Say your question again, Thomas.
You said the EMF was only forming across the bottom part of the loop of the copper wire.
No. It'd be all the way around. It would.
Okay.
So what that would say is, yeah, as you go around that loop, a bit of charge gains energy as it goes around. And so it finishes with more energy than it started. And the EMF would be, in this situation, the EMF would be generated everywhere, to be honest. Okay. All right. So we have that. And, okay. The only reason that the rectangle is important is because the question says that there actually is a physical wire there. So the EMF would be generated whether or not the wire was present. You can have an EMF in the air. You can have a voltage in the air in front of you, across your body or something. But the fact that there's a wire there means that the presence of an EMF is going to cause a current to flow. So to answer the question, they want you to find the average power. The power equals the EMF times the current. P equals IV is the rule from circuits, PIV. Only we're going to use Ohm's law to write the current as voltage over R. So we're going to write the power as the EMF squared divided by R. And we'll have to take the time average of that. All right. So raise your hand if the scenario, the kind of the story of what's happening is clear. All right. So if the story of the problem is clear, then we just have to go through. We have to first calculate the magnetic field from the wire, and it'll be a function of the distance away from the wire. Then we have to calculate the flux of magnetic field through the wire, which will implicitly be a function of time. Then we'll take the time derivative of that to get the time-dependent EMF using Faraday's law. And then once we have that, we'll use Ohm's law to get the power radiated by the wire. Okay, so those are the steps in this problem. All right, now I'm going to go over the whiteboard. Okay, so I have a wire. Sorry, the thing is really sluggish today. I don't know what the deal is. I have a wire with a time-dependent current. They tell me it is sinusoidal, so I can say it's equal to some amplitude, I max, times sine of omega t. Omega is the angular frequency, so it's the radians per second. So I know that it's 2 pi times the frequency. And since the frequency is related to the period, I know that it's 2 pi divided by the period. A second here. I'm going to try to close some programs here because the stylus is really sluggish. All right, let's see if that's better. Okay, so the omega, I have sine omega t, is related to the period and it's related to frequency when we need it. All right, so now let's continue. We first need to find the magnetic field lines, which, let's change colors. I usually am I've been putting them in red here. And I'm just going to draw them as if they wrap that way. Since the current is up and down, the magnetic field lines are going to be both up and down, kind of both orientations. So I'm just writing it out. I'm going to just pick one, and then later on we'll have to evaluate it for all times. All right. So how will we find the magnetic field around this long wire? What's the best method? Whose law is going to help us with that?
Faraday's law.
No, we want to use Amperes law.
Oh,
Faraday's law is what's going to allow us to find the EMF. We're going to use Amperes law to find the magnetic field. So Amperes law says the integral around the loop of B dot ds. What the heck? I'm sorry,
It's a nice S you got there, Sean.
Yeah. The stylus is really sluggish. Equals mu naught times the current, and the current could be a function of time. Because of the symmetry of the problem, I know I can write that as B times 2 pi r equals mu naught times I, or the magnetic field as a function of everything really is mu naught times I, which is a function of t, divided by 2 pi r. Okay, so that's the magnetic field at any radius away from the wire using Amperes law. When you use Amperes law, you have this Amperian loop which goes around with the magnetic field, and the surface it spans is perpendicular to the wire. Okay, so there's kind of like a soap bubble here, and the wire pierces that soap bubble. That's for Amperes law. Now that we have that formula, we have to deal with this rectangle. So I have my wire, and then I have this rectangle. Now it seems to be working better. And I have the magnetic field lines, which go kind of through it, like that. And I need to find the flux of magnetic field through this loop. So, because I'm going to use Faraday's law to turn that time-dependent flux into an EMF. So the magnetic flux, well, that's just defined to be B dot dA so it's a double integral. Whoa, we'll just leave that one off. Sorry. Okay, so that's the magnetic flux. And so in some of the other problems we've had, like with a solenoid, we were able to just write this as B times the area. Are we all okay with that? Does anybody want to complain? Anybody want to complain?
Wait, why can't we do that?
Why can't we do that?
So that's just the area of the rectangle, right? The A. We can just have that
Well, what's in front of the A?
differential.
Yeah. And what's out here in front?
An integral.
So that means something, right? You can't just ignore calculus. Not true. You can't do that. So this rectangle, it extends radially away. So if I drew a little patch here, I would say dr in that direction, and then I don't know, we'll call it dy in that direction. So dA, it just looks like Cartesian coordinates. And the magnetic field depends upon r, and so when you do this, when you have this integral, you're integrating over r, and so you can't pull the magnetic field out. So this becomes mu naught over 2 pi. The current only depends upon the time, so I can write that as, I can pull current of time out, but then I get the integral of, I'm going to get a 1 over r dr. Sorry, my pen's going sluggish again. Dr times dy. Wow, looks like a little kid did this. Okay, all right, so I'm integrating over r. What's that? Okay. Yeah, fair enough. Fair enough. I figured it was going to be Sam giving me some positive feedback. She likes to do that. Okay, so I've got my magnetic field. I think I've got everything in there. And so then the y integral, if you look at the problem, this is a, this is b is the length, so that makes this point a plus b, and this distance is c. So the integral over y, well, nothing depends upon y. So the integral over y is just going to give you a factor of c. And the integral over r is going to be from a to a plus b. So this is just going to give me mu naught I as a function of time over 2 pi. The y integral just gives me a factor of c. And the r integral gives me a factor of log. And it's going to be a plus b from a.
Wait,
Stop
wait,
me there.
Sean, can you do that again? The a plus, that's what I don't understand from the question, the a plus.
Okay. So I'm putting the origin, this is r equals 0.
Okay.
And I'm integrating over the area of this rectangle.
Mm-hmm. Yeah, I know you did that, but like, so like when you integrate 1 over r, that's ln r, right?
Yes.
And then how did a plus b over a?
Well, what's the outer radius? A plus b.
Plus b, okay, and then
Inner
a.
one is a. And log of a plus b minus log of a equals log of
into division. Okay.
a. And that's actually how you should always write it. When you have quantities that have dimensions, they should, the argument of logarithm, because it's a transcendental function, must be dimensionless. So even though in a math class they will say you can write it as the difference of two things, it doesn't really make sense for that to be true. You need to put it in a dimensionless quantity. Okay, so go back to my change colors. So that's my formula. So I can write this as, basically I can get, okay, so that's my magnetic flux. What does Faraday's law say?
Equals the negative time derivative of the flux.
Yeah, the EMF equals minus d by dt on the flux, magnetic flux. And so I need to take a time derivative of this, which is comes from the current term. So this is just going to be, so I'm going to have all these numbers out front. I'm just going to write them all here once here. Mu naught c over 2 pi log a plus b over a. These are all just constants as far as time is concerned. And then I have times the derivative of the current. And remember, the current was sinusoidal. So it's going to be I max, the maximum current, times, when I take a derivative of this with respect to time, I'm going to get a factor of omega. And it's going to turn sine into cosine. So I get I max times omega times cosine omega t. Whew. Good God. Is that okay? Does it make sense? Does anyone have a rechargeable toothbrush,
Yeah, I do have one.
right? And has a base, and you put the toothbrush on top of it?
Mm-hmm.
Well, this is what's happening. You have a time-dependent current coming from the wall in the base of your toothbrush. There's a loop, and you basically arrange so the magnetic field lines from the base go through the loop in the toothbrush, and that's how you get current into the toothbrush without ever having to actually have a metallic, a piece of metal that's exposed.
How about wireless chargers? Do they have
Same
anything
thing.
with
Same exact thing. This is what's happening.
and wireless chargers too?
This is the exact same thing. I mean, you would design the shape and stuff to make it optimal, but the idea is the same.
Mm-hmm.
Yeah. This one's nice because the calculus is pretty easy. Other shapes might be a little bit harder.
Oh, is that why the wireless does that have anything to do with how wireless chargers are always like they're circles basically? Is that like just a simple shape to create that?
Well, it's also easy to make because you can. So let me finish this example and we'll talk about that. All right.
Okay, and then also Sean, why was the current sine omega t?
Well, the problem said that it oscillated. It was a sinusoidal current.
Okay.
I think they gave a frequency. Does anyone remember?
Yeah, I think they did too.
Okay, so you'll have to go back and use these conversions to relate frequency to omega and period and stuff. All right, so now we have a time-dependent EMF, which generates a time-dependent current in the wire. So there's a current in the straight wire, and now there's a new current in the loop of wire. And the question asks us to find the average power. So the current, sometimes it's clockwise, sometimes it's counterclockwise. We want to calculate an average power. All right, so let's
Oh,
do
and
this.
also Sean, what is the I max? Did they give us that? The max current?
I will look here and see. They give
Oh yeah, they give the amplitude. Okay.
an amplitude. They call it amplitude.
Okay.
It's the maximum current.
Yeah.
Yep. Sorry, I lost my. There, no. The whiteboard space disappears sometimes. There you go. Okay, so now the power as a function of time is equal to, well, it's EMF times the current, but this would be the loop current, not the wire current. And since they give me a resistance, so actually I'm going to write that as the EMF squared over R using Ohm's law. All right. And now I want to average the power. So this is the power at any one time. So it's going to go like the EMF squared. It's going to go like sine squared. So it's going to oscillate between 0 and 1, up and down, up and down, up and down, up and down. And we want to compute, they ask us to find the time average of that. So we're going to average this power over one cycle because every cycle is identical. So if you know the average value for one cycle, then you know the average value over multiple cycles. And so I'm going to look at this coefficient here. Here's the EMF. I have to square all this crap out front. And then I have to average cosine squared. So, oh shoot. All right, let me look at it, stare at it, and try to remember it. Mu naught C log 2 pi I omega. So mu naught C I max log of A plus B over A times C over 2 pi. And then there's an omega. I think I've got them all. Just you not see max omega. Yeah. Okay. These are all those constants. And you have to square it because it's EMF squared. And then you have cosine squared of omega t. And then we have to average that over one period. Right? Oh, sorry, that's the EMF squared. I have to divide by R. There we go. Now we're good. So I've got EMF squared divided by R. And I have to average over one period, one cycle. It looks terrible, but if you can pull out all these constants and focus just on the cosine piece. If you think about the graph of cosine squared starts at 1, goes down to 0, goes up to 1, goes down to 0, goes up to 1, goes down to 0. And the average value of cosine squared is just going to be a half. And so basically, everywhere you see cosine squared, you can replace it with a half. And that's how it goes when you calculate these RMS values for sinusoidal things. If you want to do more,
can just ignore the omega completely.
Ignore the omega. Oh, what happens is by changing omega, you will change how long you have to average it over. So as you adjust omega, you will average it over more or less time. But the upshot is you're going to average over one full cycle, regardless of what omega is.
Okay, yeah, that makes sense.
Right? Okay. So then I can just say that this is going to be mu naught C, everything squared, I squared max log of crap squared times omega squared divided by 4 pi squared. And then you get 1 over, there's an R there, times 2. Right? The resistance only comes with one factor, just going back to the original formula. And that's what you get. Raise your hand if you feel like you followed the logic of that. Okay, good. All right, let's talk about Mohammed's tooth, or let's talk about a phone charger. So what's happening there, I mean, I haven't cut one open, but I think all that's happening is you're going to have a base which has a coil, and this will go into the wall. And then you'll put your phone on top. And what this will have is another coil hooked up into the battery. And you're going to have to do other things too, because you're going to only want to, you're going to want to make sure, I assume, so basically you're going to have to convert the AC into a DC somehow. I don't, that'll be complicated. But the upshot of how you get the energy from the wall to the phone is the following. You get a time-dependent magnetic field from the wall, which runs through the coil in the phone. So the time-dependent current from the wall creates a time-dependent flux through the loop in the phone, which creates a voltage in the phone, and then you have to store that in a battery. And so that's what happens. Why is this? What's the weakness of using this method for transfer of energy? Can you guess?
You get less current.
Why? Well, less. Why less? Something's less.
Magnetic field is less?
Yeah. This is a dipole. how does the magnetic field go with a dipole for large distances? It's like 1 over r cubed. So it falls off fast for a coil like that. So what happens is typically magnetic fields get weak very quickly. So unless you have this loop in your phone right on top of it, or you have a very efficient phone or very long battery life, or you have to, it's very difficult to build up enough energy in the phone to make this an efficient method. And so I think that's why maybe you need a very large loop or something like that. So I don't know technically how they've got around this, why all of a sudden we're able to do this magnetic field energy transfer. I mean, the idea has been around forever, but they haven't been doing it in cell phones till recently. Hey, Brian, I don't know if you're there. Do you know why we can do this now and we couldn't before? If he's there. Hold on, I'm trying to find the chat. Not offhand. Okay. So it has to be something about, maybe it's that the newer phones don't require as much battery life as ones did. I don't know. I don't know the answer to that. So, and Thomas, I think the reason why there's a loop is just because it's, with a loop, you can fold it back on itself many times. And every time you do that, the magnetic field grows. So you could just get more flux, which means you can get bigger EMFs generated. All right. Any other questions on toothbrushes and wireless charging? I mean, you might say, well, wait a minute. If we can do this, why don't we use wireless charging? Like, have a satellite in the sky with solar panels and beam down energy and charge electric cars as we drive. Well, the reason you can't do that is because of this very fast dependence. How do we get around that in this other example? Well, in this other example, we solved for the magnetic field of an infinite single wire, and then it only fell off like 1 over r, so it was a stronger magnetic field. But that's not going to be very yeah, right. So you can get this stuff to work on short distances, but you can't get it to work for over. I think once you get past a few centimeters, basically this is just not a viable energy transfer mechanism. All right. Okay, let's talk about, there's another one. I thought it was 6. No. I'm looking at the homework problems here to get 6. Was it 6? Yeah, number 6. I don't remember this one. I'm just reading here. So the investigators are researching moving objects. The owners think it's a poltergeist. Others think strong magnetic fields. Scientific investigation, apparently, whatever. Start by focusing on magnetic fields, whatever. So using a coil made of so many turns, you use a motor to rotate the coil at a constant angular speed. So you have a coil that rotates, and then you notice that you get a voltage across it. Okay, so yeah, that's fine. This is like a generator. This is like the BPU plant. That's how that works. How many of you guys went to the BPU plant with Tim?
I did.
Okay, do you
Went somewhere? Pretty sure that's where we went though.
where they generate power, the power plant.
Yeah, with the two steam. Wait.
Yeah. So this semester, set aside all that thermodynamics crap. Who cares about that? How did they actually make power? Where did the electricity come from?
Turbine.
Yeah. Well, okay. What did that do for you?
Spins the shaft, spins the shaft. Right?
Yeah.
And then generates electricity. Oh, generates magnetic fields.
Yeah. Well, yeah. It's the same idea, right? So you go to the BPU plant. Now in this problem, there's a loop, a circular loop, but okay. And now in the BPU plant, I can't remember if they spin a magnet or the magnet's fixed and they spin the coil. I think the magnet is fixed and they spin a coil, but anyways, it doesn't matter. It amounts to the same thing. So, so you can imagine there's a magnetic field going through this loop. And then if you spin the loop with a frequency omega, well, you can imagine, so let's say the magnetic field lines are going into your eye. If the loop is like this, then lots of the field lines go through the loop. If it's rotated 90 degrees, none of the field lines go through it. If it rotates more, the field lines go through it, but in the opposite direction. If you rotate again, it's zero. So you get lots of flux, no flux, negative flux, no flux, positive flux, no flux. So the amount of magnetic flux is changing as the loop rotates. Raise your hand if that makes sense. Okay, not everybody's doing that. So, okay, there you go. So if you have a rotating loop, that's going to cause the flux through it to change, which is going to give rise to a time-dependent current. And just from simple geometry, you know the flux goes like a dot product, so it's going to depend on like omega, it was like cosine of omega t, or sine of omega t, one or the other. It's going to be sinusoidal. And that's why we get sinusoidal current out of the wall, because we have a spinning magnet or spinning loop, and that's what you get. You can either think of it as the loop is fixed and the magnet's spinning, or you could arrange it so that the magnet's fixed and the loop is spinning. I think usually it's easier to have the loop spinning than the magnet spinning, but I'm sure there are all kinds of different designs. That's an engineering thing. All right, so basically then, I'm going to assume that I've got a uniform magnetic field, and I want to evaluate the EMF. Wait, do they want the EMF? I can't remember. They tell me the EMF. They tell me the number of volts that are generated. So the EMF is going to be minus the derivative on the magnetic flux. They tell me this number. I want to solve for the magnetic field. So I write that as minus the derivative of the integral of, so I'm going to get B. The magnetic field is assumed to be constant times, it's a dot product, so B times the area.
Hey, Sean. Your mic is sounding like you're in a tunnel right now.
It's because I am.
Oh, there we go.
All right. Can you guys raise your hand if you could hear what I was trying to say here? All right, so I'll say it again. So the EMF is the time derivative on the magnetic flux. Since the magnetic field is going to be constant, that's just, the B is just floating there. I have dA, but because it's a dot product in the flux calculation, I get a cosine of the angle between the magnetic field and the loop. and it'll go like cosine of omega t. So then, so raise your hand if that makes sense. Okay. All right.
Can you re-explain the integral? Like, just
Well, what is flux is the integral of b dot dA,
yeah.
where this is vector dA and vector b. So when you take, then you can, but you can use the formula for dot products to write it in terms of magnitude of b,
Oh,
magnitude dA, cosine of the angle between them.
okay, that makes sense. Thank you.
But then because this is constant and this cosine of
Shauna happened again. The mic. Wait a second. Before you say anything important.
so the magnetic field and the
Oh.
cosine of omega t are independent of the area, so they just pull out.
Sean, we can't hear you.
Wait, talk one more time.
Can you hear me now?
Yeah,
Yeah.
that's good.
I don't know what's happening. I keep hitting this mute button, and I'll just write it. Can you guys follow what I did there?
So how did you get rid of the integral without integrating?
Nothing depended upon, so that the
Oh,
area,
you're integrating with, okay, yeah,
it
okay.
just pulls out. So this just becomes minus b times pi r squared plus, there's an omega sine omega t. Okay? And in the problem, they give you this, and I think they give you all this other stuff. And, or they give you the maximum. What do they give you? They tell you the maximum voltage. And that comes when this is just equal to 1. When the sine of omega t is 1. So you can get b equals that stuff. All right? Raise your hand if that made sense. Okay. Okay. So that's how a generator works. You spin something in the presence of a magnetic field, and it generates a time-dependent EMF. Okay. All right. So those are the examples I wanted to go through for that assignment. I wanted to talk a little bit about electric and magnetic fields. When you have, so I worked through the videos, I solved the equation. So I really just want to talk about the answer so you kind of can see what happens. In the video, I solved for a plane wave. And a plane wave is a wave which, so it's a wave in 3D that is constant, sorry, which, say it differently, which it only depends on one coordinate. Okay, so think about a plane in 3D. Oh, sorry, let's undo that. So let's imagine I've got, so what's going to happen is we're going to have a wave. Like, what if I write this? The electric field is some number times, sorry, z hat times cosine, and it'll be like omega, no, like some number k times x minus vt. So look at this thing. It points in the z direction, but it only depends upon the variable x. Okay, so can you kind of try to picture that? So if you were to plot level curves of constant magnitude electric field, the level curves of this only depend upon x. They don't change in y or z. So that means if you were to plot out the shape of kind of surfaces of constant magnitude, it would sweep out a plane. Raise your hand if that makes sense. Okay. So, okay, good. All right, so the thing about these electromagnetic waves is the solution that I worked out, the electric and magnetic field will point in the z and y direction, and the wave travels in the x direction. So let's lay down some bits, kind of fundamental things about waves. So just some comments on waves. So plane waves can be written, will be functions of x plus or minus vt. If it's this is really a 1D wave, but it turns out even though the waves I wrote down in the video are in 3D, they behave as if they're only 1D because they're plane waves. So I have two choices of signs, minus and plus. What would be the difference in the two waves, or the two kinds of solutions? Well, think about this. What if you made a graph of the function versus x, and let's say at time equals 0, and it looks like this, right? And then I ask you to sketch the graph when time equals, I don't know, 1. What would happen to the graph? If you, at time equals 0, it looked like this. When you plug in time equals 1, what happens to it?
So does it just shift? Is that what you're saying?
Which way?
The right, the
Yeah.
first one.
So this one's going to move to the right. So this is a right mover. And the other one's going to shift to the left. It's a left mover. Okay? All waves, or all 1D waves, can be written like this, x minus vt. It's a function of that one combination. It can have other things in the problem, but everywhere there's an x, right next to it has to be plus or minus vt. They're always grouped together in the wave equations. On the other hand, we have that the waves can be written as, I don't know if I did cosine or sine, but cosine of some number k times, well, we usually write it like this, kx plus or minus omega t. K is called the wave number, and it is 2 pi over the wavelength, the size of the wave. Omega is angular frequency. which equals 2 pi over the period, or 2 pi f. This will solve the wave equation, but on the other hand, it has to be, but only if it's a function of this combination. So it must be that if you factor kx plus or minus omega t, if you factor out k, and you write this as k times x plus or minus omega over k times t, in order for this function to look like one of these functions, it only works when I look at the argument of cosine. It must be that omega over k equals the speed of the wave, which turns out to be the speed of light for electromagnetic waves. Right? So the ratio of omega and k in this wave solution gives the speed of light. And then you can rewrite that using these various different things. So that turns out to be the same as saying that c equals lambda over the period, or c equals lambda times the frequency, or omega over k. These are all equivalent statements. And this is true these are actually true whenever you have waves of light, even if they're not planar waves. You can still characterize it with a wavelength and a frequency and write that down. Is that okay? So the thing that happens with light is that all the waves travel with the same speed, but different kinds of light will have different frequencies. But because the speed of light is constant, if you make the frequency big, you must shrink the wavelength. So increasing the frequency is the same as decreasing the wavelength. And conversely, if you were to lower the frequency, that's the same as increasing the wavelength. So all the types of light are really, they're all the same thing. They just differ by the size of the wave or the frequency of the wave. You can say it either way. So does anyone know what we call really long wavelength waves?
Visible light. Radio waves. Wide.
When we talk, radio waves are just waves of light that have really long wavelengths. Anything longer than, I don't know, your thumb width, that's a radio wave. Anything that long or bigger. Then we have micro. Then we have infrared. Then we have Roy G. Biv. Which for me is Roy. Oh wait, I forgot my B. I don't know. Roy G. B. I. V. I never know what these are. I just call it. I really have Roy G. Bip because I just see purple. Anyway, and then you have ultraviolet, or as my kids say ultraviolet, and then X-rays, and then gamma. These are the wavelengths for these are about the size of a crystal, or maybe large atomic scale. So use X-rays to try to probe a lot of like crystal structures in chemistry. Gamma rays start to be nuclear sized, and then you can work out their corresponding frequency, because you know the product of wavelength times frequency is the speed of light. Raise your hand if you knew that all these things are really just light waves. Did you know that before this class? Some people did, yeah. All right. So that's how that works. They're all the same. Yeah. Yeah, I don't know how much more I can tell you in 5 minutes. The subject, this is, to be honest, conceptually, this is the most interesting part of the class, is how the electromagnetic fields work and come together. I just want to show you a picture of what they kind of look like, I guess. I don't know. I'll share that with you. I thought I had it. Oh, there we go. All right, so you'll see this kind of picture drawn lots of places. So this is a planar electromagnetic wave. The blue is supposed to represent the magnetic field. So the magnetic field is going back and forth in the, it kind of points in the X direction. The electric field goes up and down in the Y direction, and then it travels in the, sorry, the electric field goes up and down in the Z direction and is traveling in the Y direction. And they're always perpendicular away from charges. When they're near a charge, then the angle between the electric and magnetic field doesn't have to be 90 degrees. But when it's near, when it's out in the air, that's what it looks like. And that's what light is. You should be having a big question right now. Is there some question? Well,
I mean, I'm just confused on why they're perpendicular to each other.
oh, that's easy. It's the same. We just saw it in Faraday's law. So the which way did the magnetic field lines went this way, but then the EMF or the electric field was going around a loop perpendicular.
Okay.
Right. It's just that it's the same perpendicularity. In the videos, I explain it in detail. There's some Calc 3 going on there. I'll write down Maxwell's equations in their kind of full form. It turns out you can write everything we've learned this semester as this. The divergence on the electric field is the charge density over epsilon naught. This is Gauss's law for electric fields. The divergence of the magnetic field is 0. Gauss's law for magnetic fields. The curl of the electric field is minus the time derivative on the magnetic field. That is Faraday's law. And Amperes law, as corrected by Maxwell, is this. Okay, so you have to watch the videos for the derivation of this. But everything we've been talking about with Gauss's law and Amperes law and Faraday's law, they can all be expressed like this. And what you can see is that the magnetic field is perpendicular to the electric field because of a cross product.
Hey, Sean.
Yes.
I don't really remember curls that well from Calc 3. Are they kind of like moments? Like, are they like is it kind of like a moment kind of thing? Like, where it's just like the the radius cross?
Well, no. It's partial x hat plus partial y hat plus partial z hat. Treat it as a vector and take the cross product, say, with the electric field. And so that's going to give you x hat times the partial of y on ez minus partial z e y minus y hat partial partial x e z partial z e y plus z hat partial x e y minus partial y, e, x. So you just pretend that the gradient operator is a vector, or not pretend, you just use the fact that it is and take the cross product with it, acting on the electric field. So what's really happening is we're using, you remember there were Green's theorems in Calc 3? That's where this is coming from. Use Green's theorem to relate flux to a divergence. And anyways, it's in the video. I can't really do it in 2 minutes here, but that's where it's coming from. Yeah. So the thing that always puzzled me when I was a kid about this is why, if electromagnetic waves are, E and B waves, if this is light, why don't I see, when I look in the room, why don't I see, the light flickering up and down, up and down, up and down? Does anyone know why? It's okay. When you plug in numbers, the frequency of the oscillation is huge. It could be going through 1 million cycles a second. And our brain only operates at best on millisecond timescales, probably on hundredths of a second timescale. So what that means is, in the moment that we have a perception, we can't resolve things that take place in less than, let's say 1,000th of a second. If two things happen within 1,000th of a second, we can't visually separate them. And in this case, the frequency is so high, in 1,000th of a second, you might have 1,000 oscillations. So what we perceive as light is not the individual waves. What we perceive as light is actually the time average of these waves. And that's why in the sapling question, they keep asking about time averages. That it's the optic nerve, but even that, there is it's the optic nerve, but there's also the time just in the brain, as far as the whole thing. I mean, neurons don't process, they might be able to get to a 10,000th, maybe. I don't even know. Basically the time scale for neurons is in the thousandths of seconds, millisecond time scale. And so you're just not going to physically be able to do anything less than that. So anything built out of nerves, that's going to be the upper limit of what you can do. Yeah. So what we perceive is not the individual wave. What we perceive as light is the averaged out effect. And that's why light will look continuous, or look uniform and constant to us. It's because we're looking at an average over 1,000 cycles. So yeah, that's what happens. I'm over time, but one last thing I want to say. There is a vector called the pointing vector. Sapling actually calls it the intensity vector, and I don't know why no one else does that. The pointing vector
Sean, you spelled pointing wrong.
No, I did not. His name, this is how is a French guy, I think. That was his name. But the pointing vector points in the direction of propagation. So it points in where the vector's going, where the wave is going. So I did not misspell it, but it's convenient that it sounds the way it does. The pointing vector points the way the light goes. The symbol for it is S, and it is equal to 1 over mu naught E cross B. So Thomas, remember, so the electric and magnetic fields are perpendicular, and if you take their cross product, it's going to point in the direction the wave actually moves. So the arrows of the wave point in, say, X and Y. then it will move in the z direction, for example.
Oh, okay.
And the units, what this actually measures is this is the power per area, in a direction. So if you wanted to know, like, so what you would do is if you had a surface here, you would calculate the integral, you calculate the flux of the pointing vector, and that would give you the power that hits the surface. But basically, what I really want to say is, in everyday terms, when you calculate the magnitude of S and you average it, so you use the same thing, RMS value, or you replace sine squared with a half. The average value is what we call intensity of light. So there's one question where they ask about the intensity vector, and they call it S, but it's actually the pointing vector, and you should take the cross product of E and B. It can also be related to energy, the rate of change of energy, and also you can relate it to a pressure. The pointing vector will tell you the pressure of light radiation on you or on something. So anyway, all right, I think I need to stop there. I'm trying to cram in too many kind of concepts without deriving all the connections. So you have to watch the videos to see where they're connected. Are there any last questions we have before ending this?
Sean, like, what are your like plans for the rest of these?
Okay, yeah. So let's comment on that. So first off, when do you have exams next week?
We have one for DiffEQ, I know that.
Do you know what day?
I'll just say Wednesday, I guess, because it's definitely not Monday.
Okay.
And then because I think she said that we're not going to have a final in that class, so we're just having a final, like this is our last test covering the last material.
Yeah, that's okay. So that's what I'm going to do too. I'm in this class and in dynamics. We're going to have a last test. We're not going to have a cumulative final.
Yeah.
Hey Sean, have I ever mentioned that you might be my favorite teacher?
Now.
Now, yeah. He takes back all those things he said about me. So we're going to, oh crap, I should have stopped recording. We could have really given Shane a heart attack. So we're going to have a final test on this stuff for next week. And I just want to try to time it so that not all your tests are at the same time. And Brian, it'll be the same thing for Physics 1. We're going to do one more. Hopefully I can get everything up to date this weekend is the plan.
Are we going to have like a day to do the exam?
So yeah, I think we're going to do like last time where I give 24 hours. So if you guys have DiffEQ on Wednesday, then I will make this class have an exam on Thursday. And
Sean, you said that's it. One last exam, no labs, no anything else.
Right.
Okay.
Right.
Good.
And then Brian, I will have you do the Physics 1 test on Friday, if that's okay, of next week. All right. And then as far as dynamics, I think for dynamics, what I will do is, wait, you guys, he isn't here. Does anyone know, has anyone heard, is there a chemistry final for organic? Does anybody know?
He hasn't told us what it is yet, but I think we have one.
Is it going to be, so you don't know when?
Yeah, he had us take like a survey to figure out. I think it's going to be next Friday, maybe.
Okay. So then for dynamics, so it'll only catch Shane on that. We'll do the dynamics test on the Monday, like the last official day of classes, the Monday of finals week. We'll do a test on dynamics.
Do you know what day is that exactly?
I do not.
So
So that would be, so I'm looking at,
they start from Monday 11, right? And then
so I'm thinking that for this class, you guys will have a test on Thursday. For Physics 1, Brian, you'll have a test on Friday, the 8th. So it'd be 7th, 8th, and then I gotta pull up the calendar. For dynamics, the test would be on the 11th. All right.
and that would be what chapters for like dynamics?
Dynamics would be 16, 17.
Okay.
And this class, so for this class, you should study inductance, Faraday's law, Amperes law. The only questions I would ask about Maxwell's equations are very qualitative. Okay, because obviously we are just flying so fast at this point that we're not going to do anything. There would not be anything technical on electromagnetic radiation. So just very qualitative stuff. You should know how to use Ampere's law and Faraday's law to calculate magnetic fields, and Biot-Savart.
Okay.
Biot-Savart, Ampere's law, Faraday's law, to calculate magnetic fields, and then to calculate EMFs that they might produce.
So whatever comes after inductance, right?
What? Say it again, Mohammed.
So everything from inductors and inductance and everything after that, all the videos on there.
Well,
you
it
could
could
do
be
that.
Biot-Savart. Everything from Biot-Savart on.
Yeah.
And know how to calculate inductance. And the key examples for that are an infinite solenoid and a toroidal solenoid. Those are the most famous examples.
And Sean, so like for these classes, they would transfer like normal classes, right? Not because we didn't do a final, they're not going to transfer them or something.
Right. Yeah, they don't care.
Yeah. All right.
Because when you transfer, you don't report a final exam grade anyway.
Oh, but yeah, I don't know. I guess you're right. Yeah.
All they do is transfer a letter grade. So that's it.
That's good. Don't want to be repeating all these classes next semester.
Yeah, I know. You guys, unfortunately, your group, well, everybody who's a student right now, it's going to be a mess when you guys transfer. And I mean, those people will have the same issue. So they're going to know. I mean, all around the world, everyone's going to know that you have to manage this thing.
Yeah.
Okay, Brian says Wednesday, Friday work better. Okay. All right, we can do that. Okay. Any other questions about this stuff? Unfortunately, the stuff here at the end is kind of anticlimactic because it's hands down the coolest, most counterintuitive thing, but we're having to go through it really fast. So for next week, I guess on Tuesday, I thought that would be a review day if you want to ask questions and about any of the topics that could be on the test.
All right.
Okay.
For the test, where do you think we should study from? Like, I don't know, videos, or like concentrate more on like questions like on sapling or stuff like this, or questions that you do on videos?
I would do videos.
Videos?
Yeah.
Okay. All right. Because questions on sapling, I think they're like way harder than the videos one that you have so far, I guess.
So are you saying I should make them harder? Okay.
No, I'm just saying, though.
Okay. Great.
You're doing good.
Yes, please. All right. Okay. All right. If there are no other questions, I'll let you guys go. Have a good weekend. All right.
Okay, see you, Sean.
See ya.